Alright troops, Yoker Uni presents Physics.
Hello there, Valdo back again to help you out for your higher physics, especially all you that totally buzzed up your prelims and you look big champ if you got a crap mark. Get over yourself and study like nobody has ever studied before. This video is all about laser beams going through a thing called a diffraction grating, but I need to tell you a couple of things first though. We're not going to figure out how a mad laser beam actually gets made, that's in another lecture about emission spectra and nearly balls, mad atom model and all that stuff, right? We're going to just say a laser beam is a source of monochromatic light, which is pure coherent. Monochromatic comes from the Latino language, isn't that? Mono means one, and chromatical means shiny, I think. Anyway, coherent is something Deco isn't on a Friday, and a Saturday and a Sunday. In fact, Deco isn't coherent on any day that ends in a Y, never mind though. Coherent in physics means the same frequency, amplitude, phase and all that stuff, right? So a laser beam is only made for one colour or one frequency. That means it will be a pure wave in that, so let's go over what a wave is in physics. A wave is how energy is transferred from a source to some other place. Light and water and crap are transverse waves. Sound is longitudinal. All waves have a frequency, which is how many waves you have in 1 second measured in hertz. They've got a period, which is the time for one wave to pass a point. Frequency is 1 early period, by the way. The wavelength is called lambda, and some amplitude thing called the amplitude. Everything that's a wave has to do 4 things, which I like to call the 4 things a wave has to do. They have to reflect, they have to refract, we're on it another time. They've got to diffract, which is waves pure bending around objects and crap. And the big kick in the nads is they've got to interfere. 2 coherent wave sources making waves beside each other, and they're going to interfere with each other, alright? You can get your mad coherent wave sources by having 2 sources which match each other in every way, or you can have a big super plane wave which you pure fire through wee slits to make circular waves, and that by diffraction. If 2 crests or troughs for each wave meets at the same time, then they're going to add to each other and make the wave bigger. That's called constructive interference. If the crest of a wave meets the trough of another wave, then they cancel each other out, and that's called destructive interference. If we pop a big screen so the waves are going to hit it, then we call the pattern that you make on there an interference pattern. Water does this, so does light, and so do electrons. Even though light itself was actually a wee photon wave thingy packet, if you up the filing through one at a time, you'll get an interference pattern still. Same for a wee 1 electron at a time, which is pure mental quantumness. Right, so if you get 2 wave sources or 2 slits which make 2 sources of waves, then you are going to get an interference pattern. If you measure the distance for the wave sources to the bits where you get constructive and destructive interference, then that's what we call a mad path difference. If your constructive interference is dead in the middle, then there's no path difference, and that's called a 0 order maximum. If you have a swatch along the pattern, then you come to a wee mad minimum, which is the destructive interference. Then you come to another maximum, which is called the first order maximum. Then another wee minimum, then a second order maximum, and so on. This does go on a bit on both sides, away from the 0. Turns out there's a wee mad equation thing to figure out how far it is between the maximum and minimums. If you use a wave with a shorter wavelength, then the distance between these wee mad maximums and minimums goes down. By the way, you need to keep a heavy edge on the number of these wee mad maximums and minimums, like 0, 1, 2, 3, 4, 5, 6, 7 and that, right? Back to lasers now for a wee bit. Laser stands for light amplification by the stimulated emission of radiation. If you have all the words included, it should make up the word lapsior. But it doesn't have the right ring to it, you know what I mean? Laser it is. The wee guy who pure made up the laser used microwaves, no light, so it should actually be called a maser. Thing is though, we say all your mad EM spectrum is called light. Just the wee bits we call light are the bits we see, but it's all light, alright? Lasers pure get a bad snash about them, so they do, like in films and that, like James Bond, when he's lying on the table, and Goldfinger's pure shoving the laser up the table towards Bond's 0017, and he's like, "You expect me to talk?" And the wee Ginger's like, "No, big chap, I pure expect you to die." Lasers, man, are everywhere. Your CD Walkmans, your car radio, your DVD player, your Blu-ray, your PS3, your Xbox, all have lasers in them. By the way, as a wee guy that sells them doing Clydebank Market, all of them for £100, can't you beat it? Lasers have different classes, like Class 1's a wee buffed laser for things in your home. Class 4 lasers are like, no point covering your eyes, wee man, it'll burn through your horns and burn through your eyes and out the back of your skull. That's the kind of danger we're talking about in Yoker. Right, cause of the pure wee mad wavelengths of laser light, if you bumped it through a double slit, you just get a big smudgy line, because all your mad maximas and minimas are dead close together on that. We use a thing instead called a diffraction grating, which is hundreds of wee slits. We get the number D, which is the distance between your slits and your diffraction grating. If you know how many slits you've got per millimetre, then you can fart about with some arithmeticals and get your mad D number out. On your mad screen for your interference pattern, you'll get your mad 0 maximum, then your first, your second and your third and so on, order maximums, but they're all spaced out, you know what I mean? By the way, we pure ditch the minimas. The reason is there's hundreds of them between the maximum spots, so we just say, nah, can't be bothered. In actual fact, there's the number of slit minus 1 number of minimas between your spots. There's a wee factoid. Before I pure get ripped into the equation for this mad crap, I need to show you a wee mad video I made up to show you this on action. So there's your wee mad magic video then, showing the handle Valdo and all your mad different things with this diffraction grating crap and lasers and all that, right? Here's a wee mad equation thing for it then. G sine theta equals n lambda. For the bit in the video where I moved the screen to 1 metre away, here's the mad numbers for it and how you need to work out your wavelength for the laser light. Obviously, there's hundreds of errors in there and uncertainties, so we're just going to look at them just now because remember, Valdo doesn't do errors. So, for the wee mad equation then, if you use different colours, then your mad spots would get closer together. So if you have like a green laser, then a blue laser, the spots would move in the way towards the middle. If you were to use white light, which is pure made up for the rainbow colours, by the way, Roy G. Biv invented the rainbow, then you would see some wee mad spectrums being made where the maximum should be. The zero's still white because all your mad colours still fall on the 0 point, and when you add them up again you still get white light. That's why that bit's there, you know what I mean? Red diffracts the most and violet the least. If you had a refraction through a prism, then you would get only one spectrum, and red would refract the least and violet would refract the most. Capiche? Something that pure uses a wee mad diffraction grating is a wee mad thing called a spectroscope, which splits up your light for things like stars or gas lamps and gives you a mad zero maximum bright line in the middle. Then you have your mad spectras either side of it. Different gases give off different line spectras, but more on that another time, you know what I mean? So that's it. There isn't really much more to talk about diffraction grating, so that's all you're getting, big chap. So there you go then. So for now, it's just a big catchy Versace.